Hello, my name is Andrei Ivanov, and in this screencast I will describe my third-year project, Evolutionary Generative Adversarial Networks. The project is supervised by Dr. Ting Mu. In recent years, generative adversarial networks, or GANs for short, have found huge success in various image generation-related tasks, but still suffer from a lot of training problems. In my project, I extend a previously proposed modification of the GAN called the evolutionary GAN, which aims to overcome these problems with evolutionary methods. Firstly, I will describe the problem of generative modeling, which is the general problem my approach is aiming to solve. In generative modeling, given a dataset of examples of some real-world phenomenon, the goal is to learn to generate new samples from the phenomenon. For example, given a dataset of images of cats, the goal is to learn to generate new, previously unseen pictures of cats. The current state-of-the-art approach for generative modeling is the Generative Adversarial Network, or GAN for short. The GAN consists of two neural networks, a discriminator and a generator. The goal of the generator is to learn to generate images like the images from the training dataset, and the goal of the discriminator is to learn to distinguish between real images from the dataset and fake images from the generator. The two networks play an adversarial game where the generator tries to trick the discriminator into thinking its generated samples are real. In the past 5 years, GANs have found success in a large number of applications. Here's an interesting example where a GAN was used to perform style transfer between images. For example, on the left, the zebra pattern was transferred to the horse and vice versa. Despite their success, GANs are still notoriously hard to train. They suffer from three main training problems. The first one is training divergence, which is the case when the discriminator and the generator keep getting worse with training. Then we have mode collapse, which is the case when the generator gets stuck on generating a single example. And the last problem of GANs is that they rely on heuristic tricks specific to each application. To solve these problems, previous works on GANs primarily focus on presenting different loss functions for the generator, but each loss function has its own disadvantages. My work is based on a recent paper which suggests using evolutionary techniques to overcome the discussed training problems. In the proposed EGAN model, we have a generation of generators which evolves in an environment regulated by the discriminator. In particular, each parent generator creates children by updating its weights according to different loss functions, also called mutations. The goal behind combining mutations in this manner is to overcome their individual weaknesses from the original GAN model. Then, each child generates a batch of images. The discriminator then calculates the fitness of each child, the fitness being a quantitative measure of how good-looking and diverse the images are. The fittest children move on to be the parents in the next generation. Through this evolutionary process, the model ensures it obtains better generators in each generation. My contribution on top of the evolutionary model is the following. First, I provide a TensorFlow implementation, fine-tune the lower-level details, and propose multiple optimizations. Furthermore, I compare the performance of the EGAN with the performance of DCGAN. DCGAN is the current most widely used modification of GAN. I conduct my experiments on the MNIST and Fashion MNIST datasets, which are datasets of handwritten digits and hand-drawn clothes respectively. Finally, I analyze the internal properties of an EGAN and aim to provide intuitive explanations behind the advantages and disadvantages of the model. I will now present the results of my experiments. Firstly, my experiments show that compared to the DCGAN, the EGAN is able to produce meaningful results with a much simpler neural network architecture for the generator and the discriminator. For example, on the MNIST dataset, the DCGAN requires layers of batch normalization in the generator to stabilize training. On the other hand, the EGAN only needs the most basic convolution layers. With this simple architecture, the DCGAN is only able to produce random noise, whereas my model is able to produce distinguishable digits. Furthermore, I show that the EGAN introduces an improvement in terms of speed of training. Even though the DCGAN is faster than my model per iteration, the EGAN is able to reach meaningful solutions much faster. Let's consider the first 40 minutes of training on the MNIST dataset. While the DCGAN is only able to produce random shapes, the EGAN already produces samples roughly resembling digits in the first 10 minutes, and by the end of the 40-minute interval generates completely recognizable digits. However, I find that the DCGAN is better in terms of image quality. Even though my model is able to produce meaningful images faster, the DCGAN eventually ends up generating better looking images. In this example of training on Fashion MNIST, the DCGAN slowly improves and by the end of training it produces sharp and clear images. Whereas the EGAN manages to create some blurry fashion items at the beginning, but after a point the quality of images starts deteriorating. This phenomenon ties in with my final result. Even though the EGAN reaches a solution quickly, after a certain point it destabilizes. This is best observed through the loss functions of the generator and the discriminator. In the case of DCGAN, both losses are relatively uniform without large fluctuations. This means that the discriminator and the generator are balanced and continuously learn from each other. In the case of EGAN, after a certain point in training, this balance of the discriminator loss and the mutations is destabilized in different ways. In the particular example in the slide, the discriminator loss drops too low and the mutation losses start increasing instead of decreasing. This can be interpreted as follows. The discriminator became too powerful and the generator stopped receiving any useful feedback.